Hello everyone, I am Dr. Sirajul Faizi. I welcome you in my YouTube channel. Today in this video, I am going to talk about aliphatic electrophilic substitution reactions. So, what is aliphatic ele- electrophilic substitution reactions? So, let us start learning of aliphatic electrophilic substitution. Aliphatic electrophilic. So, aliphatic electrophilic substitution reactions are related to carbanions in the same way as nucleophilic substitution reactions are related to carbocations. Try to understand terminology. Aliphatic electrophilic substitution reactions are related to carbanion and nucleophilic substitution reactions are related to carbocations. So, electrophilic substitution reactions have been much less studied than SN reactions, nucleophilic substitutions reaction. So, in electrophilic substitutions reactions, the entering group and the leaving group are the electrophile, that is Lewis acid. The electron pair of breaking bond remains with the substrate and is used to form a new bond to the entering electrophiles. So similar to aliphatic nucleophilic substitutions reactions, aliphatic electrophilic substitution also proceed through a unimolecular or bimolecular or direct displacement mechanisms. So you can see here first unimolecular mechanism SE1. So SE1 substitution electrophilic unimolecular mechanism. Substitution electrophilic unimolecular. Analogous to SN1 mechanism, it involves two steps. That is a slow heterolysis and fast combination of the resulting carbanion with the entering electrophiles. Look at the steps. So you can see here a slow heterolysis and fast combination of the resulting carbanion with the entering electrophiles. So step 1, breaking of Rx bond and formations of R minus and X plus. In step 2, R minus plus Y plus is give Ry. So electrophilic substitution can occur when the leaving group is more electropositive than carbon. Thus the common leaving groups are the metals and hydrogen. The following are some important examples of SE1 reactions. So hydrogen deuterium or hydrogen tritium exchanges. Look at these reactions. RH plus B minus, it give R minus and BH. Furthermore, R minus plus BD, it gives RD and B minus. Such exchange occurs with relatively acidic protons, that is, those alpha to a carbonyl group. However, even weakly acidic proton can exchange bases which are strong enough. Now decarboxylation. Look at here these reactions. Here formations of double bond between carbon and oxygen and breaking of carbon-carbon bond. Look at here, after breaking you will get ZCH2 minus plus carbon dioxide, and this compound further react with alcohol. It gives ZCH3 and ROH minus. So anionic fragmentation. Look at here, ZCH2 carbon O minus R prime R double prime. It gives ZCH2 minus plus RCOR acetone derivatives. It reacts further with alcohol. It gives ZCH3RO minus. Z may be acyl, may be phenyl, may be nitro, may be imine, may be X3C. Now, evidence for the SE1 mechanism. Many examples are known where the reaction follows first order kinetics. In the following base catalyzed automerizations, you can see the reactions. The rate of deuterium exchange was found to be same as the rate of racemization, and there was an isotopic effect. So, nucleophilic substitution unimolecular reaction do not occur at bridgehead carbon in 2,2,1 bicyclic system. Why? Because of planar carbocations cannot form at these carbon. So carbanion not stabilized by resonance need not to be planar. Hence, electrophilic substitution unimolecular reaction should readily occurs at bridgehead, and this is found to be the case also. So substitution electrophilic bimolecular reaction occurs with the organometallic that have a considerable degree of covalent character, or with CH bond under conditions not sufficiently basic for proton removal. There have been extensively studies with organomercury compounds, but have also been observed with a number of other metals or living groups, that is lithium, chromium, tin, iron, and cobalt. You know, my friend, aliphatic electrophilic substitution bimolecular mechanism are analogous to the SN2 mechanism. In the SN2 reaction, the attack of entering group nucleophile can take place only from the back side of the living group due to repulsions between electron clouds. On the other hand, in the elimination substitution reaction, the electrophilic substitution bimolecular reaction, the attacking species is an electrophile, which bring to the substrate only a vacant orbital causing no repulsion, and thus backside or front side attack is possible. Now, you can see here, if the attack occurs from the front side, then mechanism is called electrophilic substitution bimolecular front. And if the attack takes place from the back side, then mechanism is called electrophilic substitution bimolecular back. So When the electrophile attacks from the front and portion of it assists in the removal of the leaving group by forming a bond with the leaving group at the same time when the new CY bond is formed. The mechanism is called substitution electrophilic internal. So SE2 front, you will get the retention of conjugation, and SE2 back, you will get inversion of conjugations. Now, all the above three mechanisms follow second order kinetics, and two of them proceed with the retention of conjugation. It is not easy to distinguish these three mechanisms. A study of stereochemistry can distinguish between SE2 back and SE2 front or SEI mechanism, but it is very difficult to distinguish between SE2 front and SEI mechanism. Look at here, retention of conjugations. So stereochemistry studies on mercury exchange reaction and on electrophilic attack on CH bond have established the SE2 mechanism, but these cannot distinguish SE2 front from SEI mechanism because both involve the front side attack. So front side attack is also indicated by the fact that second order electrophilic substitution proceed very easily at bridgehead carbons and in neopentyl system where the backside attack is statically prevented. Look at here, two molecules of RHGR and XHGX forming this intermediate, then retention of conjugation stabilizes SE2 mechanism. Now, inversion of conjugation has been observed in certain which demonstrate that the SE2 back mechanism is taking place. For example, reaction optically active secondary butyl trineopentyl with bromine gives inverted secondary butyl bromide. So look at the reaction secondary butyl trialkyl plus Br2, it gives secondary butyl bromine plus R3SN Br. So R here neopentyl. Now my friends, factor affecting reactivity in SE electrophilic substitution reaction. Compared to aliphatic nucleophilic and aromatic electrophilic substitution reaction, only a small amount of carbon has been done in the field of aliphatic nucleophilic electrophilic substitution. See some examples here. So some conclusions drawn are as follows. First, effect of substrate structure. The rates of SE1 reactions are increased by electron withdrawing groups and electron donating groups. Decrease the rate for SE2 back reactions, and relativity of the alkyl group is similar to that for the SN2 reactions. So methyl greater than ethyl greater than propyl, isopropyl greater than t-butyl plus neopentyl. In fact, this pattern of reactivity can be regarded as evidence for the occurrence of the SE2 back mechanism. For SE2 front and SEI reactions, varying results have been reported. In certain cases, A branching increases the rate due to electron donating effects of the alkyl group, while beta branching decreases the rates due to steric hindrance. Now, solvent effect. As with the aliphatic nucleophilic substitution reaction, an increase in solvent polarity increases the possibility of electrophilic substitution mechanism as compared to electrophilic substitution bimolecular and electrophilic substitutions internal mechanism, which do not involve ions. The rate of electrophilic substitution bimolecular front or back mechanism are increased by an increase in solvent polarity, while SEI mechanism are much less affected. The third important point, effect of leaving group. The more polar the Cl bond, the easier is the departure of the leaving group in all the Se1, Se2, SEI mechanism. For carbon leaving group, the mechanism is usually Se1, while for metallic leaving group, the mechanism is almost always Se2 or SEI. So my friends, I hope this video will be helpful to you. If you like this video, then subscribe my channel and thanks for watching.